Hi, this video is a demonstration of calculating the heat transfers associated with heating and cooling and also phase changes. This is a little bit different from what we did in the thermochemistry unit a while back because it involves the phase change. Heat transfer, a change in temperature, the heat transfer associated with that can be calculated with the formula heat Q equals mass times specific heat times change in temp. But when there's a phase change, there's an additional thing that you need to consider. So let's look at a typical heating curve. We've got in this graph the transition from solid to liquid. Now and let's think about ice as an example. Before your ice is completely melted, you've got a system where your ice and your liquid water are in some sort of equilibrium. So that's what this picture with ice cubes and water represents. For the solid to approach that point, the solid needs to be raised to a consistent temperature of 0 degrees Celsius in the case of ice. Now, for that ice water to turn into water with no ice, energy needs to continue to be inputted into that system to melt all of that ice. Energy is required to separate those molecules of water and free them from that crystal structure of the ice. So you can kind of think of this chart here as you've got temperature on the y-axis and you've got time on the x-axis. You can also think of time as being energy inputted into the system. So for the solid to rise up to the melting point, that required an energy input. And then for the solid and liquid in equilibrium, for that to completely melt and to be all liquid, that involves an energy input as well without a change in temperature. So that's what we're trying to kind of correct for or calculate in this type of calculation. When you approach the boiling point of water, you end up with water and gas water and vapor in equilibrium. And then once the water has been completely vaporized, you've got a vapor and the temperature can continue to rise if you're continually putting energy into it. So yeah, as you go up and to the right on this heating curve, the energy is inputted and temperature rises and you go through two phase changes. Energy is released if you go backwards on this curve. And so let's think about our signs on these values. If energy is inputted, do you think the value for the heat is going to be positive or negative? Should be positive. As energy is absorbed, we consider that energy moving from the surroundings to the system, and that's a positive value. When energy is released, your value should be negative. So each line segment on this chart is a calculation. For horizontal lines, so this is when you've got two phases in equilibrium, like the solid and the liquid here, and the liquid and the vapor here. These calculations involve the molar heat of fusion or the molar heat of vaporization, also called the enthalpy of fusion, enthalpy of vaporization. And to calculate the amount of heat involved, we're just taking that heat that's expressed on a molar basis, kilojoules per mole, and multiplying it by however many moles we have of the substance. For the diagonal lines, raising the temperature of the liquid from the freezing point to the boiling point, for example, we're doing a heat transfer calculation like we did last semester. Q equals m times s times delta T. So let's look at an example problem. Example problem: how much heat is required to raise the temperature of an ice cube that has a mass of 36 grams, and this ice cube has just come out of a minus 15 degrees Celsius freezer, so its temperature is minus 15 degrees Celsius. How much heat is required to raise that temperature to room temperature 21 degrees Celsius? So besides that information, we're going to need to know a few things. We're going to need to know the specific heats for the materials involved here, both ice and water, liquid water. And we're going to need to know the heat of fusion and heat or heat of vaporization, depending on kind of what temperature range we're talking about here. Going from minus 15 to positive 21, we pass the melting point of liquid water. We're not boiling this water. So really we're only concerned with the enthalpy of fusion. Some values, the specific heat of water, we've used this a number of times before, 4.18 joules per degree Celsius in gram. But the specific heat of ice is actually less than the specific heat of water, 2.03 joules per centimeter per Celsius per gram. And the heat of fusion of ice to water, is 6.02 kilojoules per mole. So just to kind of summarize this data, I have it here in front of me. Let's just kind of think about this in the big picture. Think about kind of what's going on in this problem. Well, we've got a heating curve here. So if we think about the heating curve that I had up here earlier, temperature on the y-axis, time or energy on the x-axis, we've got ice at minus 15 degrees Celsius. And before that ice starts to melt, its temperature needs to rise to 0 degrees Celsius. Once it hits 0 degrees Celsius, it can go through that phase change, and that's when we're inputting energy to break those hydrogen bonds and form a liquid out of that solid. And then we're going to need to raise that temperature some more from 0 degrees to 21 degrees Celsius, and we won't go through any other phase changes. So, like I said, each one of these line segments is a calculation, and so I'm going to number them 1, 2, and 3. So for when we're just heating a substance and not going through a phase change, this is a heat transfer calculation similar to ones you've done before. My heat transfer is equal to the mass of the substance times the specific heat times change in temperature. Now let's look at all of our numbers that we have. Our mass, we have 36 grams. The specific heat we have, and since we're talking about changing the temperature of ice, we need to use the specific heat for ice. So that's that value there. And then recall that the change in temperature is equal to final temperature minus initial. And important to get the signs right on here, so that's why I sometimes like to actually write out that formula. And my final temperature, we're just talking about this one part of the heating curve from 15 to 0 degrees. So 0 degrees is my final temperature, negative 15 is my initial temperature, giving me a delta T of positive 15. So 0 minus negative 15, positive 15. And so from here on out, it's mostly just kind of plugging in and looking at our units, making sure they cancel out. But I've got 36 grams times 2.03 joules per gram degrees Celsius times 15 degrees Celsius. And that's going to equal 1096.2 joules. And my units on here, grams cancel and degrees Celsius cancel. So that's why I'm left with joules. Okay, so let's look at calculation number 2 here. This is the energy required to physically melt and separate out those molecules of water. And I know that it takes 6.02 kilojoules to melt 1 mole of water molecules. That's what the units on this thing tell me. And so what we need to do is figure out how many moles we have of this water. So yeah, first step, let's calculate how many moles we have. This is a molar mass calculation similar to the ones you've done before. We know we have 36 grams of this stuff. Water has a molar mass of 18.0 grams per mole. And so essentially I'm just doing 36 divided by 18, which gives me a nice round number of moles, 2. So I've got 2 moles of water. So now I know I have 2.0 moles of water. Multiply that by my molar heat of fusion, which is 6.02 kilojoules per mole. And if I were to just stop this calculation right now and multiply it through, I'd get 12.04. But I've already calculated one part of this summation up here in joules, and so it would be better off. I'd be better off to convert this to joules as well. So 1,000 joules per kilojoule will leave me with, instead of 12 kilojoules, 12,040 joules. So that's the second part of the second calculation on this heating curve. This was the first here, I'll just label that. And then the third, now we're raising the temperature again without a phase change. So we're going to use the same formula, Q equals M times S times delta T, and my 36 grams of water hasn't changed. My specific heat, now that I've melted all this water, we want to use the specific heat of liquid water, not of ice. So that's 4.18 joules per degree Celsius per gram. And my change in temperature, final temp is 21, initial temp is 0, so that's a difference of 21 degrees Celsius. And when I multiply that all together, I end up with 3,009.6 joules. Units cancel out just like they did last time. So I now have three energies, all expressed in joules, and the total energy of this heating curve of heating ice, melting the ice, and then heating the water is just the sum of those three calculations. So if we add all those guys together, 1 plus 2, step 1 plus step 2 plus step 3, that's going to give us a total, we'll call this Q tot, T-O-T, of 16,146 joules. An interesting thing, and something that you'll notice often with water, is that the heats associated with melting or vaporization tend to be larger than the heats associated with heating up the water with temperature changes. So that, for example, is why sweat cools you off. It takes a lot of energy to evaporate that water off your skin if you're working out or if it's a hot day. And so that's why sweat is so efficient at cooling your body. So yeah, mathematically here, nothing really new, but just kind of a different way to look at these phase changes.